today's training. Today's training is about the high-speed counter and the high-speed plus output. So let's begin. First topic is about high-speed counter. So I will introduce the type of the high-speed counters and the counters allocation and the counters user step, and finally the counters the relative instructions. First, our PLC supports 4 types of high-speed counter. The first one is the single-phase input counter, and the AB phase input counter is 1 times frequency, and 2 times frequency, and 4 times frequency. For the single-phase input counter, we can use some registers to change the count directions. So the counter will be count up or count down. For the AB phase input output counter, 1 time frequency, when the phrase A is on and the phrase B input is from off to on, the count will increase by 1. And when the phrase input is on and the phrase B input is from on to off, the count will be decreased by 1. And it's the same to the 2 times frequency. When the A phrase input is on and the B phrase input is from off to on, the count will increase by 1. And if the phrase A is off and the phrase B input is from on to off, the counter will also increase by 1. So when the phrase A input is on and the phrase B is from on to off, the count will decrease by 1, and the phrase A input is off and the phrase B input is changed from off to on, the count will also decrease by 1. For the 4 times frequency, you just have 4 situations to make the count up and 4 situations to make the counting down, just like the table set show. Okay, so let's look some differences between LX5V series and LX3V series PLC about the high-speed counter. For the LX3V, X0 and X1, if you use it as a hardware counter, for example, you use the C235 and the C236 and the C246, the frequency is up to 200,000 Hz. And if you use X1 and X0 as a software counter, for example, you are using HSCR instruction and HSZ instructions, the frequency is up to 100,000 Hz. And the software counter backed 4 channels is just up to 10,000 Hz. And if you use this high-speed counter as AB phase counter, the frequency is just half as the single phase. If you use LX5V series, the more output input point terminal will have more channels to get 100 50,000 Hz, and the AB phrase is also have the baud channel. So let's move on to the high-speed counter allocation. For LX5S3V, if you use one phase with user start and user reset, you just use C235 and 2C240. And if the one phrase with assigned start or assigned reset, you need to use C241 and 2C245. If you use two-phase bidirectional counter, you need to use C246 to C250. And the rest high-speed counter is for the AB phrase type. If you use it in LX5V series, you can see all the LX5V series have A-channel high-speed counter from HSC0 to HSC7. And also for the single phase or AB phase. So let me introduce how to use it. For LX3V, the first line, we need to enable these counters. And then we can use the value of this counter to trigger some other registers or some instructions. Just remember, Wecon PLC input terminal X need power is DC 24-volt signal, and the X0 to and X1 supports up to 200,000 Hz, and the X2 to X5 is just up to 10,000 Hz. If you use LX5V, it's more easier to configure it. First, we click on the parameters and then choose the high-speed counting configuration. And then we can choose which channel to use and the input mode. This is the wiring of the AB phrase encoder. So we can see the A phrase is connected to the X0 and the B connect to the X1 terminal. The COM connect to SS terminal and the power supply. Let's move on some high-speed counter related instructions. The first instruction is to comparison set. This instruction is used when the value of high-speed counter is equal to the value we preset, and then it triggered the register and the relay we set here. Okay, let me show you how we use it in LX5V series. As you can see, I enable the HSC1 and I use this HDHSC as instructions, and now the value of HSC1 is 5, and now I triggered M0, so the value will be increased. When the value is 10 equal to this one, so Y12 will from off to on. We can see it again. As you can see, now Y12 is off. And now I'm making the high-speed counter value increasing. Now it's from off to on. And there are also instruction to reset the registers we want to reset. It's DHSCR. It's the same. The first parameters we set the value to compare, and the second parameters we choose the high-speed counter device, and the last parameters is the bit of the device number to be set off. Also like this, we set it as 12. And now I also triggered M0 to increasing the value. And when it reached 12, it will reset the Y12. We can see it again. When the value is increasing, sorry, just one more time. When the value is increasing, it will from on to off. Okay, so you can see in this program, I also used some special registers such as SM431 is to show the movement direction for high-speed counter 1, and we can also make the count is counting down or counting up just by enable this special registers SM435. As you can see it now it's counting up, and then I triggered M0, M1. Now the countdown is counting down, and when I set it off, it's counting up again. And for H5 special registers, SM430, it shows when the value is reached the number we set, it will be on. And now we can see it again, the counting down. And the SM430 is still on. When it was less than 99, it will be off. Okay, it's off now. Let's move to the third instructions. It's about high-speed zone comparison. So it has 4 parameters. The parameter 1 is the comparison value 1, and the parameter 2 is the comparison value 2. It sets a compare zone. So the third is the parameter is the count device, and the 4 is the start bit for the comparison result output. As we can see it, I set a zone is from 50,000 to 100,000. So when the value of HSC0 is less than 50,000, the M0 and M10 will be on. And the value of HSC0 is greater than or equal to 50,000 and less than 100,000, M11 will be on. And when the value is greater than 100,000, the M12 will be on, as we can see it in this picture. Okay, that's the first part of today's training. Now let's move on to the high-speed output part. For the high-speed output instruction, the first part we will introduce the original return, and the second is about absolute and relative positioning, and the third is the PWM instruction, and the last one is the multi-speed positioning. The first instruction is ZRN and DZRN. Actually, it's the same instructions. DZRN just have a wider range for the parameters. If you use ZRN, the range is from 1 to 32,767. And if you use DZRN, so the value of range is from 1 to 200,000. So this instruction is to use the specific plus speed and plus output port to make the actual move to the original of actions. when the PLC and the servo drive work together until the original signal meets the conditions. So the first parameter is to set the starting speed when original. And the second parameter is for the crawling speed. The third parameter is for the near point signal. And the fourth parameter is for the output terminal. As we can see in this picture, when the object's origin return move, and when the DOG signal is received, the speed will change from starting speed to crawling speed, and when the near point signal is disappeared, the PLC stop output pass. As we can see it in this demo, the first we can depend on our requirement to set our max speed and bias speed and the acceleration time and the deceleration time and the stop mode. So when we triggered, at first there's no original signal, so it will 5 Hertz. And now it gets the signal, so just 1 Hertz output. And if the interrupt near point signal is disappeared, the path will be stopped. Okay, let's see it is in the real positioning. So at first, it output the plus in a high speed, and then I triggered you will have less speed, and when this signal disappeared, it just stopped. Okay, let's move on to the second instructions, DSCR. This instruction is that when the PLC works with the server drive, it uses the specific path speed and the path output port and the specific direction essays to move to the original actions when and until the original signal meets the conditions. So it's the same for the first two parameters, the starting speed and the crawling speed, and the third parameters is about the input number of the near signal to be input. And the fourth is the device number Y, the output path. And the last one is the directional output port. Here is some relative special registers. It's about original return mode and the original return distance. As we can see it, there are 4 modes from mode 1, mode 0 to mode 3, and the different mode have the different motion. You can choose it as your requirements. So let's see the mode 1. It will return back when he get the signal, and when after it moved for the original return distance, it will turn left again. And for the mode 2, when he get the signal, he will reduce the speed to the crawling speed and continue to move to left. And after moving the original return distance, it will move back to the right. We can see it in these pictures. The first is about the parameter. We choose original return mode 0. So when he get the signal, the speed will be reduced to the crawling speed. And when the signal disappeared, the instruction will stop output passes. And then we check the original return mode 1. When he get the near point signal, it will move to right and change the direction. And when he traveled just the distance we set here, is 200, and it will move back again. And when the near point signal received twice for the second time, the instruction will stop output pass. You can see it again. Now you can see it's 20, not 10 again, because we set the VS speed is 20. Not like this one. The crawling speed is bigger than the VS speed. And it now is moved to right. After traveled to 200 position, and when he gets the signal again, the instruction will stop. And now we can see the original return mode in mode 2. It also reduced the speed to the BS speed. It's bigger than crawling speed, so it's 220. And now he will travel the same direction about 200, and then change the direction. As you can see now, the direction changed. And when the signal gets again, it stopped output passes. Okay, you can also see this program in the picture. When X2, the signal is on, the frequency is just changed to 1. And when he gets on for the second time, the instruction is stopped. Okay, let's move to the absolute and the relative positioning. The first is about the DVIT and DDVIT instructions. This instruction will output the specific number passes when the interrupt signal will received, and then it will stop. The first parameters is for the numbers of output passes, and the second parameters is about the frequency of output pass. And the third is for the output pass port, and the fourth is about the running direction output port, and the last one is the interrupt signal. We can see in these features. So at first, when the instruction running, it will output pass. So when the interrupt signal received, it continues sending output pass. But when the number is reached our set value, and it will stop. We can see it in this program. The frequency I set is about 100,000 Hertz, and when the M5 triggered, the instruction continued to output 400,000 passes. So the triggered. So when the output pass is reached 600,000, the M5 will be on, and the instruction will stop when the output number, pass number is 1 million. Okay, as we can see it. Now M5 is on, it will continue to output 400,000 passes, and now after that it will stop. So you can see the value. It's just near to the 1 million passes. We can see it again. For now, I just stop the instruction. You can see M5 is triggered now. And when I triggered M1 again, this instruction will continue to output 400,000 passes. So when the instruction stopped, the value of SD880 will reach 1.1 million. Yes, as you can see it. Now let's move to the DRVI instruction. This instruction is a positioning instructions, and the mode is relative mode. The first parameters is the specific number need to be output. And the second parameter is about the frequency. The third is about the output device. And the last one is about the direction output port. As you can see it in this picture, if the current position is point B and I want to move it to the point C, 300, I just need to set the parameter 1 as 150. So it will move from here, point B, to point 3. Okay, let's see it in the real program. As you can see it now, the D3300, I set the value is 2000, and the frequency is 500, and the output terminal plus output terminal is Y0, and the direction port is Y1. And now the position is 0. When I triggered M1, it will move from 0 to 200. And I also use some special registers SM880. It will reset M1 when the instructions, when the output pass finished. So now when I triggered M1 again, the position will from 2000 to 4000. And as you can see, during this time, Y1 is on. And now I want to move back. So I set negative 2000. And I triggered. You can see the direction is still off all the time. And the position is from 6000 to 4000 now. I trigger it again. It's from 4000 to 2000. So this is how the DDRVI instructions work. So Also, instruction for absolute positioning, DDRVA. Actually, the parameters is the same, but the movement distance is from the original. Origin is 0, so it's called absolute drive method. As you can see, if we want to move the position is from some point to point 10, we just adjust the value of the first parameters as 100. So if we set as just 100, it will move from different position to the same position, ending position. Okay, let's see the other demo. Actually, it's the same demo. I just made a change here. It's from DDRVI to DDRVA. So now I set the position we want to arrive. For example, 5,000. And then I triggered M1. You will move it from 0 to 5,000. And now, if I trigger M1 again, it will no longer to output. Y0 will not output pass. So if we want to change the position for 200, and then trigger, it will from 5,000 to 2,000. And if negative 1,000, it will move from 2,000 to negative 1,000. This is how DDRVA works. Okay, let's move to the PWM instructions. PWM instructions is used to output and set the on time in a specific. And you can see the 3 parameters. The first parameter is the on time stone, and the second parameter is for the circle. And the third is the output device, the terminal. As you can see in this instruction, it's very easy. So I set the circle is 300 milliseconds, and the on time is 100 milliseconds. So the waveform diagram is like this. But PWM also have a premiere mode. Actually, the parameter is the same, but it have a special registers. Here I used Y0, so I set SM897 on, so it will change to the premiere mode. So now the same parameters I set, K100 and K300, and you can see the circle is the same. 300 milliseconds, but the on time is just 1/10 of the circle, just 30 milliseconds now. So this is the difference between the Premiere mode and original mode. The last instruction is about PLSR, the multi-speed positioning. You can use this instruction to output a multi-segment output path. So it has 3 parameters. The first parameter is the starting address for the D registers. And the second is about the output terminal. And the third is the direction output port. As you can see, this instruction parameter configuration table, if I set parameter 1 as D0, so D0 is the number of path segment. For example, we need 4 part output frequency in a time, and we can set it as 4. And the D2 to D3 is the first segment output frequency, and the D4 to D5 is the number of paths in the first segment. And the D6 is for the first segment waiting condition. We can have no waiting condition, or waiting for time, or waiting for a signal or a trigger signal. D7 is the first segment waiting register type. If we choose a waiting time, so it can be a constant value or a deregistered value for the time. And if we're waiting for signal, we can choose B X register or M registers or S signal registers or Y registers. It's the same for the trigger signal. And the D8, D9 is for the constant value or waiting registers number. D10 is about the operation mode. You can choose a relative mode or absolute mode. The rest is up to the how many segment paths you want. For example, if we need 3 passes, the first part, the frequency is about 20,000 Hertz, and the number of paths is also 20,000, and we're waiting for the signal is M2. Here we set D6 as 2. We can go back to check. 2 means we wait a signal when it was on, and then we can check which signal, which register we choose. So here we focus on D7 is 1, D8 is 2. So let's move back. 7 is 1, so the signal register is from register M, and the register number is 2. so it's M2 here. So this part is for the first segment. And from D12 to D18 is for the second segment. The frequency is about 10,000 Hz and the number passed is 40,000 Hz, 40,000. And the waiting signal D16 is X, so we're waiting for a signal when he was off. And the register and the 17 is 0, 18 is 2, so it's X registers and the value, the register number is 2. So it's X2 here. So if we don't need waiting conditions like the third segment, so we can just set D26 as 0. So the waveform diagrammer will be like this. When we triggered M1, the first, it will output 20,000 passes, and then waiting for the M1, M2 signal, it will continue to output 40,000 passes. And when the X2 signal is from on to off, when you keep it off, so it will continue to output another 60,000 passes. As you can see it in this mode. Okay, let me show you in the demo. As we can see it, 3 segment, and the first part, the second part, and the third part. So now I triggered M1. It will output 20,000 passes. And now I triggered M2. It will continue to output another 440,000. So it reached 60,000. And now I disabled the X2 signal. Here I connect Y2 to X2, so I disabled Y2. It continued to output the rest 100 passes. Okay, this is how the PLSR2 instruction works. This is our training today. Thanks for your watching. And tomorrow we will continue to discuss about the float point introduction. See you next time.